Welcome to the first lecture of this course, Statistical Thermodynamics for Engineers. This will be the first lecture of the series, so of 60 lectures that we are going to provide. Initially, as we start, let us look at the bigger question first, that what is statistical thermodynamics? Now, at this point in your career, probably you have always dealt with macroscopic systems. Now, these macroscopic systems could be, from a scientific or engineering viewpoint, this could be like your piston cylinder arrangement or your gas turbines or whatever device that you can think of. So, in all those cases, you have analyzed the problem, using certain methods, which in this case are the thermodynamic methods, right? So the analysis of macroscopic systems usually will involve, conservation equations, the field equations, thermodynamics and stuff like that. Now, if it is, for example, it uses principles from classical mechanics, it also uses principles from electromagnetism, and it uses principles from thermodynamics. So this is how all systems have been analyzed. All macroscopic systems are usually analyzed. So we are going to deal in this particular course with systems which are of thermal in origin, thermal systems basically. So for example, gas turbine is one such thermal systems, because these thermal systems will utilize thermodynamics, fluid mechanics, heat transfer, etc. So your heat exchangers, everything comes under these thermal systems. So in order to understand this, understand the classical thermodynamics, you should also recall that classical thermodynamics is inherently little limited sometimes to explain the simplest thermodynamic behavior of a system. Or say it can be gaseous system, it can be liquid, or it can be solid, whatever it is. So if you do not consider the microscopic part of such a system, you cannot adequately, that means the atoms and the molecules, if you are not able to handle them or treat them well enough, it will be almost hard to understand the full extent of thermodynamic properties, what is thermodynamic equilibrium, so on and so forth, right? So for example, if we ask the question that what is the influence of temperature on transport properties such as viscosity or thermal conductivity, you need to know that how temperature actually influences these kind of properties, in what ways. So this elementary viewpoint is what will be covered in this statistical thermodynamics course. Now, any particular thermodynamic system is composed of atoms and molecules. So atoms and molecules, so if you look at the particular page, you will be able to get a good thing. So let's take any system. It is composed of, these are your atoms or molecules, whatever you call it, right? Now, these atoms and molecules, they all move around, as you know. They move around in different directions. If they are placed in a container, this is like a container, for example. Okay. Now, even the simplest of a system, say if you take 1 cc of a perfect gas, okay, that contains 10 to the power of 19 atoms or molecules. So bookkeeping becomes a very difficult task because you are dealing with a huge number of particles. And not only you are dealing with a huge number of particles, in order to describe this particular phenomena, you have to know the position and the momentum of each of these particles. So you need to know what is the momentum and what is the position of these particles, right? If you know these, then you can evolve how these particles actually move, and essentially you would be able to describe a macroscopic thermodynamic system. Now, the properties of these individual particles, can be only obtained through quantum mechanics. So if you look at if you ask the question, how about the properties of these particles, right? So they come from quantum mechanics, which most of us are familiar with, that what quantum mechanics is. So they have their origin in quantum mechanics. Now, one of the most important results when you deal with a quantum mechanical system is that the energy of any single atom or molecule, say this is an atom or a molecule, okay? If this is the atom or the molecule, then the energy E of this atom or the molecule is not continuous but discrete. So the energy E is not continuous, and essentially it is discrete in nature. That is the very basic tenet of quantum mechanics. Now, because they are discrete in nature, it is discrete because of the reason that these atoms or the molecules, okay, they only can have certain distinct energy values. So they cannot have all energy values. They only can have distinct energy values. So this atom or the molecule, they can have energy, say E1, E2, E3 and stuff like that, but not continuous, that between E1 and E2 they cannot have some kind of an energy, say which is 1.5 E1. Okay, so based on this, if you just plot the spectrum, say you take an emission signature from a gas, okay, and this is the wavelength. So you have, basically you are monitoring that how this energy actually varies. You will find that the spectrum is composed of stuff like that. Very narrow but very discrete lines. These lines do have a little bit of a finite width, which we will cover, that how that width actually comes from. So, for example, this is the discrete changes in the energy that is stored by an atom or a molecule. So the height of each of this line, if you take a look at the height, this is the height of each of this line. So the height of each of this line basically reflect the number of particles that are causing that emission signal. So it's basically more the height, more of the number of particles which actually has that particular energy. So that is how the number of particles is actually related to the height of this emission signature, right? So the point of view of classical or statistical thermodynamics is that the number of relative particles can only be determined by what we call some kind of a thing called probability theory. But we will come to that a little later. But as we can understand that in quantum mechanics, all the spectrum that you see over here, they are discrete, and the height is related to the number of atoms or particles, or atoms, molecules, which are essentially particles, the number of particles that are causing the sharp change in the height. Now, the total energy of if I write, this is the total energy of a single, say, molecule or atom, whatever, okay, can be taken as the sum total of the energies, okay, caused by what we call translational mode. Translational, okay. We will come to what these means in a second. Translational, then of course there is rotational. There is vibrational, and there is of course electronic. Okay, so these are the sources of energy. Okay, so that's what is a translational energy. Translational energy is nothing but the kinetic energy of the molecules center of mass. Okay, so the kinetic energy of the molecule center of mass is basically what is called the rotational, what is called the translational mode of energy. Now, the other sources, for example, rotational, if I take rotational now, what will be rotational? Rotational basically describes the energy that is stored by the molecular rotation. So the molecular rotation, the energy that is stored by the molecular rotation is what actually determines the rotational mode of energy. The vibrational mode is the energy that is stored by the vibrational bonds that holds the molecules, right? And the electronic mode is basically the energy that is stored by the motion of electrons within the molecules. So you can understand, so each of this mode is very distinct. Translational mode is nothing but the kinetic energy of the molecules, right? The vibrational mode is basically the bond, the vibration of the bond of the molecules. Then rotational is the rotation of the molecule, right, across different axes. And electronic is basically the energy that is stored by the electrons due to its motion around, the energy that is stored by the electrons in the molecule. So as you can understand that by combining all these energies is what actually gives you the total energy, or the total internal energy, if I might call it. This energy is internal energy. Okay. So internal energy basically is, of course, usually we say that this is the vibrational plus rotational plus electronic, whereas the external mode, E external, is basically the translational mode. That is how these things are differentiated, just for bookkeeping purpose. This has got, so the external is basically the translational, because this involves bulk motion of the molecules, okay, not the rotation about relative to its own state. Okay, so what we can do is that by combining predictions from quantum mechanics with experimental data that is obtained via spectroscopy, it turns out that we can evaluate what will be the contribution from each of this mode. Later on, when we actually do a little bit of work on absorption spectroscopy and similar type of spectroscopic techniques, you will know exactly what I mean. So you can combine what we call, measurements from spectroscopic measurements combined with quantum mechanics. We can actually evaluate what are the contributions from each mode, and therefore we can determine the microscopic properties of these individual molecules. So such properties actually include bond distances, for example, the rotational or vibrational frequencies, the translational or electronic energies, etc., etc. And then by employing statistical methods, we can average this across all particles to calculate the macroscopic properties. So you understand, from quantum mechanical calculations, we understand what are the contributions of the different modes, the vibrational, the rotational, electronic, translational. And then by using statistical methods, we basically average it across the entire system, which is basically composed of millions and millions of atoms. And then that will lead us to the final macroscopic properties. The macroscopic properties, which is what we learned in our classical thermodynamics. Right? So temperature, internal energy, entropy, these will be some of the properties that we can actually understand from these statistical methods. So let's look at a particular figure as a roadmap of what we are supposed to do. So on one side, you have quantum mechanics. So what does quantum mechanics do? Quantum mechanics looks at, the properties of individual atoms / molecules. Okay, it is microscopic. Of course, it is microscopic, and it is discrete. Okay, so these are all hallmark of quantum mechanics calculation. Then on this side, you have classical thermodynamics. So classical thermodynamics. thermodynamics, which basically looks into the properties of an ensemble, of an assembly basically. Ensemble actually has a different connotation, assembly, properties of assembly of atoms and molecules. So you're not concerned about, individual atoms and molecules anymore. This is the other end of the spectrum. And it is macroscopic, obviously, because these are properties that you can see, you can measure, you can feel, and they are continuous. Usually they are continuous. Okay, so the bridge between these two is provided by the statistical thermodynamics. So stat thermo acts as a bridge between these two. So how it does is basically there are two. We were going to see that stat thermo has got two postulates, which we are going to see in a second. Postulates. Okay, and it banks on probability theory. That means we have to learn a little bit of probability, so to say. Okay, so as you can see, so this is the roadmap, right? So as we can see that the framework for statistical thermodynamics can be divided into three conceptual themes. Okay, so stat thermo, okay, will have three conceptual themes, and we can kind of go through them one by one. The first is equilibrium, stat thermo. Okay, so that equilibrium stat thermo will focus on independent particles. Okay, so by independent particles we mean that there is no molecular interactions among particles of interest. You can see, so there is no molecular interaction between the two, between the particles of interest. So this is equilibrium stat thermo. Right. Then of course the second one. So examples of this will be, like for example, ideal gas. Okay, there is also pure crystalline metal, black body radiation, etc. These are all part of this. The second one is called the second one after is also called equilibrium statistical thermodynamics. This is also equilibrium stat thermo, but this comes with a catch. The catch is that now the particles are dependent particles, right? So by dependent particles, moment we say that these are dependent particles. So dependent particles would essentially mean that now there will be interactions among the particles, right? So there will be intermolecular interactions. Okay, so there will be intermolecular interactions in this case when we are dealing with dependent particles. Okay, so these are, for example, real gases, polymers. These are all examples of this. Real gases, for example, gases, polymers. Okay, so these will be all part of this second one. Okay, so now that we know that this intermolecular interactions becomes very important at higher densities, that is when the particles are close together, they are brought close together. And because there is a lot of mathematical difficulties now, because the macroscopic properties now will require a lot of semi-empirical type of calculations. The third conceptual theme is called non-equilibrium. Remember the word? Non-equilibrium stat thermo. Now this is a little dicey because here we are concerned with the dynamic behavior that happens when a system shifts from different equilibrium states. So the dynamic behavior. So this is basically the dynamic behavior of a system when it of a macroscopic system, basically macro system, when it goes from one equilibrium state to another. Okay? From one equilibrium state to another. Okay, so this arises when well, there are different ways to analyze it. There are time correlation methods which deals with this non-equilibrium thermodynamics. But in this particular thing, we are going to look at basically dynamic processes that can be linked with the kinetic theory of gases. Kinetic theory, basically, not kinetic theory of gases. So we can get some deeper understanding of fluid mechanics and heat transfer and molecular diffusion, which basically is the dynamic behavior of a system as it goes from one equilibrium state to the other. So with all these things, keeping all these phenomena in mind, okay, all this drama basically, all this drama and all these things, you would be actually able to calculate from atomic and molecular properties the thermodynamic properties of real systems. So from atoms and molecules all the way up to the thermodynamic properties of ideal gases, real gases, metals, and all these things, you can actually calculate using this. So the idea over here is that in statistical thermodynamics now, therefore, we have to look into the probability part. We have to learn a little bit of probability before we go on and start evaluating the behavior of these kind of systems. And so basic probability that comes with maths that you may have studied in your undergraduate or basically in school days, we are going to do a rehash of those. And before we get into this, before we move on and try to understand the dynamic behavior and how we can best analyze this kind of systems. So in a nutshell, what we have covered in the first lecture is basically we have always dealt with macroscopic systems. And macroscopic systems, we have all looked up the properties of such systems. We know what is the internal energy, entropy, all these things. We have looked up thermodynamic tables, stuff like that. But we were never really, clear that how those properties actually evolved, what was the origin of those properties. That we were never certain. And because we were never certain about those, the understanding of those, the insights was not there. So therefore, we have to deal with microscopic systems, understand what is happening at the microscopic level. And once we understand what is happening at the microscopic level, you will be able to get a very clear idea that how that can be translated to the macroscopic level. Okay, so the second thing that we learned is that any thermodynamic system is composed of atoms and molecules. So there are even a 1 cc of a gas, ideal gas, which is very dilute in nature, will have 10 to the power of 19 atoms or molecules. It's a huge number, huge amount of bookkeeping, and you need to know the position, you need to know the momentum of these particles, you need to know the properties of these particles. So the properties of these particles comes from your quantum mechanical calculations, and one of the main feature of the quantum mechanics is that the energy of these particles are discrete, because this is what we are going to use later. The energies are discrete, they are not continuous, because each particle can only have certain distinct energy levels. It cannot have any energy that you want. As a result of that, we come to the concept that these energies are basically quantized. So when you deal with a single particle, atom or molecule, you will find that they will have these energies like translation, rotation, vibration, and electronic. Out of that, except translation, all the other three are considered to be internal modes, whereas translation is considered to be an external mode. So all these energies are somehow related to how this atoms and molecules actually is. And that comes from your quantum mechanical calculations, right? So using, sometimes you use quantum mechanical calculations with this with spectroscopic measurements to get an idea that what these systems actually are, right? How these systems, what are the properties of these systems, and then use statistical tools now, okay, to average it across a whole lot of particles and then find out macroscopic properties. And as we learned that the classification of statistical thermodynamics is also important. Most of the time when you are dealing with equilibrium statistical thermodynamics, it can be based on independent particles, that means the particles just move around without seeing each other. That happens in the case of ideal gas or in the dilute limit. But on the other hand, it can be dependent particles. In that case, you need to know the intermolecular interactions between particles. And thirdly, it can be non-equilibrium thermodynamics, where you actually are concerned about the dynamic behavior of a system as it migrates from one equilibrium state to the other. And this is where your fluid mechanics, heat transfer, all these things comes into the picture. So this is the excitement. This is what it is, and this is how statistical thermodynamics can actually help engineers to find out what will be the next step forward. So based on this, we are going to then in the next class look at the probabilities, that what are the probability and statistics basically. We're going to look into probability and statistics, and once we go into probability and statistics, we will introduce concepts like what is a mutually exclusive event, what is equally likely events, and all those things. And once we understand those, it will be much easier for us to know the next few steps, that how statistical thermodynamics is based on this probability and statistics. So this will be the topic of the first lecture. So and as a matter of fact, we are prescribing the book of Norman Lorendau, as was shown in the introductory video. So the Norman Lorendau's course can be actually looked up, and that book is what we are going to follow pretty rigorously throughout this particular course. And we will assign homework problems and assignments which we need to do and turn them in, so that we can get an idea. There will be exercises which should be given at regular intervals. So that is a part of the course curriculum. And we have already, in the introductory video, if you look at it carefully, we have already covered now what is the syllabus, what is the motivation for studying this particular course. By this time, you already know a little bit of this already. So we will take a look at all of those in the next class. So this is where we end the first lecture, and we will see the next lecture, which will be on probability and statistics. Thank you so much.